All right, so in the previous section, section 2.2, we constructed an expression to find the slope of a tangent line at a given point for a function f of x, as opposed to of getting the slope of the secant lines, which requires 2 points and not exactly one single point. And we also looked at an application to illustrate what that rate of change is, the instantaneous rate of change, for a situation in which we found the instantaneous velocity of an area in this case at a particular time. So now we are going to use the same limit definition, the same limit definition to find derivatives of other functions. For a while, we're going to forget about this average rate of change, instantaneous rate of change. We're going to call it the derivative for now on. And yes, we're going to use the same formula, f prime of x, denoted f prime of x. That prime means derivative, and this this is the expression to find the derivative. F of x plus h minus f of x minus the original function and divided by h. So let's use the limit definition to find the derivative of each function. So we're going to do 3 examples in which we will use the limit definition, which, yes, it's going to be a little bit painful in some cases. I'm not going to lie to you. But again, this is something that we have to do. It's something that we have to go through. And of course, if you have taken a calculus class in the past and you know the differentiation rules, well, the derivative for example A, f of x, 2x plus 3 minus 7x, you can find the derivative in basically 2 or 3 seconds. But in this case, we're going to spend uh, more than just 2 or 3 seconds to find this derivative. All right, so this is what we're going to do. Let's set up the limit expression here. So to find f prime of x, this is the limit h approaches to 0 of f of x plus h minus x. So in this case, the original function evaluated at x plus h, and minus the original function, the whole thing divided by h. All right, so let's actually simplify. Let's simplify this. Okay, let me make this a little bit more compact. Okay, so let's simplify this expression. And let's divide by x, by h rather. So yes, this one we are going to use a bunch of space here. Well, so we need to expand this binomial cubed right here. All right. How do we expand the binomial cube? So let me make a side note here. On the previous video, we recalled how to expand a binomial square, which is a squared plus 2ab plus b squared. All right, that is the squared of the first term plus twice the product of the first and the second plus the second squared. Now for a plus b cubed, we're going to do the following. A cubed plus 3a squared b plus 3a b squared plus b cubed. Where is this coming from? Well, I mean, is it something that you are supposed to memorize? Well, not necessarily. Well, depending on the instructor that you may have for intermediate algebra, it's not necessary to memorize, but it's good to memorize. It's one binomial expansion that it's good to have in our memories. However, this, at least you saw it back in college algebra, when you went over the binomial theorem. So, and the pattern here is that the power of the first term decreases. So we have a 3, a 2, an invisible 1, and then 0, it disappears. We no longer have that power of a. And then for the second variable, see how increases from, well, b to the 0, b to the first, b to the second, and b to the third. That was the pattern for the variable and the coefficients 1 to 1 on the binomial squared and 1, 3, 3, 1 for the binomial cube. Those came from Pascal's triangle. Well, that's I really don't want to get really in depth into into the binomial theorem. Nevertheless, I'm gonna leave that video, that extra video, if you want to revisit the binomial theorem from college algebra or pre-calculus, whenever you have taken that class. So let's expand the binomial. This will be a limit of 2 times the binomial cubed. So if we apply this binomial cube a plus b to x plus h, this will be x cubed plus 3hx squared plus 3h squared x plus h cubed minus 7x minus 7h, and then minus 2x cubed plus 7x. So what are we doing here? Well, I'm distributing the negative 7, and I'm distributing the negative sign, which changes the sign of everything inside of the parentheses here. So the whole thing over h as h approaches 0. And then limit as h approaches the 0, let's distribute the 2 here to every single term. And this is 2x cubed plus 6hx squared plus 6h squared x plus 2h cubed minus 7x. Well, actually, we can start canceling terms. This one cancels right now, so we don't need to write this one anymore. And minus 7h minus 2x cubed. The whole thing divided by h. And also we can cancel more terms. We can cancel 2x cubed with negative 2x cubed. So that's going to narrow down to limit as h approaches 0 of 6h. So notice in this case 6h x squared, 6h squared x, 2h cubed, and 7h. All these 4 terms have a common factor of h. So the common factor is h, and 6x squared plus 6hx plus 2h cubed, or rather, 2h squared minus 7. And then the whole thing over h, and this is ultimately what we wanted to obtain, to cancel these h's. And now that those 2 h's go away, we're safe to plug in the limit for h equals to 0. So limit 6x squared plus 6h x plus 2h squared minus 7 as h approaches to 0. Well, what happens in this case when h approaches to 0? So what we want here, so when h equals to 0, this term is going to go to 0. This other term is going to go to 0. And limit h, oh, no more limit because we already plug in the value for h. So our final answer is 6x squared minus 7, which can be easily obtained using the general power rule that of course we will discuss later in this section. Let's look at another example. Let's take the derivative of f of x equals to the square root of x. Alright, so again, limit definition, limit f of x plus h minus f of x over h as h approaches to 0. So what we want in this case is the limit of the function evaluated at x plus h minus the original function over h as h approaches to 0. Well, over here we are in some sort of a dead end, because if we wanted to cancel that h in the denominator, well, there's no way we can factor it out from the numerator the same way we did it over here. Back in the previous example, we were able to cancel out those two h's, but as a GCF. However, not in this case. What are we going to do here? Well, you might remember we already did something like this back in section 2.1, where we multiply the numerator and the denominator by the conjugate of the numerator. That is, we rationalized the numerator. So let's do that then. And, well, of course, also back in section 2.1, we discussed that we could either FOIL this, but that's going to take a good minute to complete. Instead, if you want to do it that way, you should get the same result that I am about to obtain. However, you might want to take advantage of the property a minus b times a plus b, and I also mentioned back in that video, back in that section. And, well, let's do instead limit h approaches to 0, and that's the square root of x plus h quantity squared minus the square root of x quantity squared over the product. Let's just multiply this across h times this quantity. And my advice, again, the same advice that I gave back in that section: do not distribute, just multiply across without distributing. And this will be limit h approaches to 0. Well, what's going to happen here? This index of the radical cancels the square, leaving us with x plus h, and this other radical cancel this square, minus x. And see now how these two are going to go away. These are going to get canceled. The denominator will remain the same. H times the sum of the square root of x plus h plus root of x. And this will be limit. So when these two disappear, well, we're left with limit h approaches to 0 of h over h square root of x plus h plus root of x. And again, these two goodbye cancel, leaving us with a 1 in the numerator. And when at this point where we cancel these two h's, we are good to go. We are safe to plug in to compute the limit at h equals to 0, because it will no longer cause any trouble to give us at 0 in the denominator. So limit, we're left with limit square root of x plus h plus the square root of x as h approaches 0. And we're good to go and plug in for h equals to 0. That is square root of x plus 0. All right, so what are we doing here? We're plugging in h equals to 0 over here. And well, underneath the first radical in the denominator, x plus 0 will simply be x, square root of x plus square root of x. And guess what? These two are like terms. So 2 square root of x in the denominator. And that is the derivative of the function f of x equals to square root of x. 1 over 2 square root of x. Yes, a little painful, a little bit of a painful process that it's very involved. It requires using techniques from all that we learn in algebra, such as a backwards factorization, well, a backwards difference of squares, rationalizing numerators by multiplying numerator and denominator by a conjugate. All right. And let's do one more using this kind of a painful process. Well, let's see. So the derivative of f of x equals 1 over x. Okay, so limit as h approaches to 0 of 1 over x plus h. All right. Well, let me actually, well, that's fine. I skipped the formula this time and then minus 1 over x. The whole thing over h. And I also did one example very similar to this one back in section 2.1 where we needed to multiply numerator and denominator by the least common denominator. So you might want to think of this h as h over 1, and we need to find the LCD, which is the product of all the different denominators, right? This one, and that one. Well, and in this case, it's going to be x times x plus h. So that's the LCD. So let's multiply by x times x plus h and divide by x times x plus h. So in this case, what we're going to do here is multiply x times x plus h with this fraction and x times x plus h with this fraction to obtain the following. Limit of x times x plus h times 1 over x plus h minus x times x plus h times 1 over x. The whole thing divided, yes, in this case, we will just multiply across h times x plus h. And again, do not attempt to distribute this, because if you do that, you won't be able to see what are we going to be canceling. You'll see. I believe I gave this piece of advice back when we covered section 2.1. h approaches 0. Now let's simplify this complex fraction, and in this case see how this x plus h cancel, this x with this x cancel, and the complex fraction is no longer a complex fraction. It will be a simple fraction, which will be limit h approaches to 0. We're left with x minus x plus h over hx times x plus h. And in this case, well, be careful here when distributing the negative sign. That's going to change the sign of everything inside of the parentheses. x minus h over hx, x plus h. Limit, this cancels, boom, boom. H approaches the 0. hx, x plus h. And see how that h gets cancelled. And we're no longer going to have that h equals to 0 in the denominator. So now we're going to have the following. We are going to end up with limit -1 in the numerator, x times x plus h. In the denominator, h approaches to 0. And in this case, we're safe, we're good to go and apply or compute the limit for h equals to 0. Plug it in here, and this will be limit, or no more limit, by the way. When we compute the value, when we plug in the value, we no longer we no longer denote this limit because it's already evaluated. So x plus 0, that's a -1, x times x, which is -1 over x squared. And this is the derivative of the function f of x equals to 1 over x, which is 1 over -1 over x squared. Well, before I'm almost finishing this first part of the section, but I would like to finish this video talking about existence of derivatives. Well, so geometrically speaking, well, so we'll look at the derivative again at so let's take back that geometric concept, which is the slope of the line that is tangent at a given point. However, there is a problem in some situations in which the derivative does not exist, or it's undefined. Rather, the derivative is undefined. So, for example, when we have a function that is discontinuous at f of x is discontinuous at a value x equals a. For example, for this function f of x equals 1 over x, notice there is a vertical asymptote at x equals the 0. And well, it's an asymptote, there's no point in there, so that's one of the situations in which the derivative it's undefined, because the function is undefined at that value as well. Again, let's look at the second example, for which when we have a graph of f of x that has a sharp corner at x equals a, like this function right here, f of x equals x minus 3 times x to the 2/3. Of course, if you look at this function, well, over here there's some sort of a linear behavior. That slope will always be the same at any point. And also here slope equals 0. There's another slope, another slope, another slope right here, different slopes. However, the problem with sharp corners is like this point over here. Think of trying to stand at a very spiky place. You know, it's a very dangerous place. It's not a very steady place. You can fall from that place very easily. All right, and that's what happens here. So at this point, we may have this tangent, we may have this tangent, we may have this tangent, infinitely many tangents actually. Then for that reason, the derivative is undefined, so we cannot differentiate the function at that value. The other case, the third case scenario, is when the tangent line is vertical. And that's the case for the function cube root of x. For the function cube root of x, there is there is a point right here for which we have actually a vertical tangent line. And well, what is the slope of a vertical line? Yes, well, the slope for a horizontal line we said it was 0, but the slope of a vertical line is undefined. And that's a fact that we bring up from intermediate algebra. Undefined for the vertical line. All right. And well, I would like to split this section into 2 videos as well. So I think this is a good place to quit for this one. I will see you for the rest of the section on the next video.